In the bitter winter of 1941, the fate of the Soviet Union was being measured not in months, but in days. The German war machine had clawed its way to the very doorstep of Moscow, its spires visible to advancing troops. Entire Soviet armies had vanished, consumed by the Blitzkrieg. As the temperature plummeted to 30 below, the nation's capacity to fight back was freezing solid. Its industrial heart had been ripped out. Factories were hastily disassembled, packed onto trains, and shipped eastward, far from the front lines. There, on the frozen soil of the Urals, they were being pieced back together. The state cried out for production. It demanded machines. It demanded power. And, as always, the state demanded that innovation follow the rigid lines of approved procedure, sanctioned by a council. Inside a drab administrative building in the temporary capital of Kuibyshev, a panel of the USSR's top aviation minds was gathered. They were evaluating a document from a 31-year-old engineer whose name was unknown to them. The paper outlined a new aircraft engine. It promised a staggering 1,800 horsepower from a 46-liter displacement, a self-contained unit weighing an unbelievable 600 kilograms. The head of the committee recited the figures with deliberate slowness, the kind of repetition used to confirm an absurdity. He set the proposal down, his gaze fixing on the young man before him. "This isn't an engineering plan," he declared. "It is a work of fiction." The young man's name was Arkady Volkov. He held no diploma from a celebrated academy. He had no friends in high places, no influential figure to champion his radical ideas. He was the son of a factory mechanic from a small industrial town, raised on the floor of a workshop. His childhood was spent diagnosing and mending broken equipment with intuition and scavenged parts. By 12, he could pinpoint a mechanical flaw by its unique sound. By 15, he had resurrected a diesel pump that seasoned professionals had condemned as scrap. He taught himself complex thermodynamics from a lone, borrowed book, studying by the flicker of a candle after grueling 12-hour shifts. He filled the margins with notes until they were full, then began scribbling on the inside covers. To the decorated men of Soviet industry, he was a ghost, a nobody. Standing in that formal chamber, he seemed utterly out of place, a man who had stumbled into a meeting far above his station. But he hadn't. He was summoned, evaluated, and rejected in less than an hour. The committee's official finding was a single typed line. The proposal violates established thermodynamic principles and is unworthy of state investment. A handwritten note scrawled in the margin by a senior member added a final insult. "This man belongs in ground transportation." Volkov walked out of that building into the brutal winter air. He had traveled for 2 days by train for this meeting, rehearsing every calculation, every potential argument, and for his efforts, he received the predictable scorn that established power reserves for outsiders who dare to dream differently. He stood on the frozen street and made a choice that would ripple through the entire war. He would build his engine anyway. This was not an act of defiance born of arrogance. Volkov was not a man for grand gestures. He was a practical mechanic who thought in terms of tolerances, pressures, and temperatures. What he possessed was more potent than simple self-belief. He had proof, not a theory on paper, but a deep, intuitive certainty forged over 15 years of fixing things everyone else had abandoned. He had run the numbers 1,000 times. He was certain it would work. The fact that an entire committee of experts disagreed was, in his mind, not a reason to stop. It was merely another complication, like a sheared bolt or a warped cylinder. Head, you find a way around it. You must always find a way. He returned to an abandoned compressor station on the edge of the aircraft plant where he worked. The building was a hollow shell, its heating pipes long since frozen and burst. A layer of frost coated the concrete floor. Most of the useful equipment had been stripped and sent to frontline factories. Volkov requested permission to use the derelict space from the plant director. The director, overwhelmed by impossible quotas and chronic shortages, barely acknowledged him. "Fine," he muttered, "just don't get in my way." Over the next weeks, Volkov quietly built a team. It was not an official team with assigned resources. It was a conspiracy. Two young machinists, Yuri and Pavel, barely out of their teens, had been relegated to the night shift with little to do. He showed them his plans. He explained the science, why it should be possible. Then, in a low voice, he laid out the risk. If they were discovered, it would mean charges of sabotaging the war effort by misusing state property. Both young men agreed on the spot. They were freezing, they were restless, and they saw in Volkov the unmistakable spark of someone who knew exactly what he was doing. The genius of Volkov's engine wasn't a radical new metal alloy or a complex piston shape. It was a concept so deceptively simple that the engineering establishment hadn't failed to make it work. They had dismissed it as impractical before even trying. The technique was aerosolized liquid cooling. To grasp its importance, you must first understand the central challenge of combat aircraft engines. An engine's power comes from how tightly it can compress the air-fuel mixture. Greater compression means a more powerful explosion, but compression also creates immense heat. Excessive heat in the intake air causes the fuel to ignite erratically, a violent, uncontrolled detonation instead of a smooth burn. Pilots knew it as knock. It was the sound of an engine tearing itself apart from the inside. Every major nation was battling this problem. More power meant more heat, which meant detonation. The universal solution was to build bigger, heavier engines with more cylinders. It was a strategy of brute force. But what if you didn't need more metal to fight the heat? What if you could just remove it? Volkov's idea was an injector system placed after the supercharger. It sprayed a fine mist of an alcohol-water mixture directly into the highly compressed, superheated air before it entered the cylinders. The liquid instantly vaporized in the hot air stream, absorbing a colossal amount of thermal energy. Evaporation is a profoundly powerful cooling process. That energy had to be drawn from somewhere. In Volkov's system, it was drawn from the intake air itself. The temperature of the compressed air plummeted by nearly 100 degrees in a fraction of a second. This created a dense, cool, oxygen-rich charge that rushed into the cylinders. The engine could now operate at compression levels that would have destroyed any conventional design. And the weight cost was minimal. A small tank, a simple pump, a spray nozzle. That's it. The committee had rejected the idea because it violated their assumptions, not the laws of physics. They were men who built careers designing within known limits. Volkov's experience was different. His reference point was a broken tractor in a frozen field, and the only question that mattered was, how do I make it work with what I have? Necessity had forged the most advanced engineering mind in the Soviet Union. The trio labored through December and into the unforgiving cold of January. The chill was so profound that the lubricating oil in their machine tools would solidify. Each morning began with a blowtorch to thaw the equipment before any work could start. They scavenged components. Volkov would later admit it was theft, plain and simple. A carburetor from a wrecked plane, bearings from a Lend-Lease crate that was marked damaged. A dynamometer coupling from the factory's main test bay, which hadn't been officially logged for weeks. He gave his own rations to Yuri and Pavel, arguing they were younger and needed the energy. He lost 8 kilograms during those weeks, but he hardly felt it. On January 15, 1942, they prepared to start the engine. The three of them stood in the frozen chamber, pre-dawn darkness pressing on the single frosted window. Volkov made one last fuel mixture adjustment by feel, like a master violinist tuning his instrument. He had checked every bolt. every seal, every wire the night before. He checked them again at midnight and again at 4 in the morning. He knew the line between a functioning prototype and a catastrophic failure was often a single, overlooked detail. He would not be careless. He would be perfect. He gave a nod to Yuri at the starter. The engine coughed, then caught on the third try. For 12 seconds it ran rough, then something shifted. The vibrations smoothed out. The engine's tone deepened, settling into a powerful, steady hum that Volkov had only heard in his head during calculations. A clean, controlled burn, free of the ragged edge of an engine straining at its limits. The alcohol injection kicked in. Volkov's eyes were fixed on the intake temperature gauge. The needle began to drop. 30 degrees, 60. It swept past 80 and kept going. He felt a breath escape him he hadn't realized he was holding. The dynamometer climbed to 1,840 horsepower. He had promised 1,800. The engine had surpassed his own fantasy. Yuri threw his arms around Pavel in celebration. Pavel laughed, then glanced at Volkov, suddenly unsure if laughter was allowed. Arkady Volkov stood perfectly still, his eyes locked on the gauge. Then he calmly picked up his notebook, turned to a clean page, and began to record the data. Yuri later recalled that Volkov's hand was rock steady. 3 days later, the missing dynamometer coupling was noticed during a routine audit. The discrepancy escalated. Within 48 hours, Volkov was summoned to face the plant's security chief, charged with misappropriation of state resources. He walked into the hearing carrying a briefcase. Inside was his entire case, 11 months of calculations, 60 pages of handwritten thermodynamic theory, photographs of the prototype, and the official dynamometer logs from the test run, stamped by the machine itself. He laid the documents on the table. "Before you decide my fate," he said, "I suggest you call the State Aviation Committee and inform them of your findings." The security chief was a pragmatist, a common product of Soviet wartime industry. He wasn't interested in ideology. He was interested in not making a career-ending mistake. He studied the numbers on the log. He looked at the photographs. He picked up the phone. 2 weeks later, Arkady Volkov was once again standing before the same state committee that had dismissed him. The same chairman, the same faces, but this time, he was not there to ask for permission. He was there to present results. He had brought his engine. He had also brought Yuri and Pavel, both scrubbed clean and standing stiffly, trying to look like model workers and not co-conspirators in industrial heresy. The engine itself sat on a trolley in the hallway. A few committee members had inspected it before the meeting, returning with pensive expressions quite different from their looks in December. The presentation took 6 hours. Volkov explained everything: the theory of evaporative cooling, the compression dynamics, the fuel consumption rates. He addressed every single objection from their first meeting, countering each one not with argument, but with hard data, a measurement, a result. Twice they stopped him and demanded he recalculate a formula on the spot. Each time, he did it from memory. After 6 hours, the chairman surveyed the room, then turned back to Volkov. He offered no apology. Soviet officials did not apologize in 1942. He simply said, "Prepare the production drawings. You will have authorization within 48 hours." It arrived in 36, but a working prototype is not a factory. Production was a new war, and Volkov discovered its brutal realities immediately. The gap between a single, hand-built machine and an assembly line running around the clock under immense pressure was not a gap, it was a chasm. The first production batch of engine castings was riddled with porosity, tiny, invisible bubbles in the metal that caused the cylinder walls to crack under stress. The failure rate was a catastrophic 40%. The plant director told Volkov that the committee's newfound patience was wearing thin. Volkov spent the next 4 days on the foundry floor, not in his office. He stood by the casting stations, watching the workers, observing the process. He identified 3 tiny deviations in the mold preparation and adjusted the cooling protocol for the aluminum alloy. Within 2 weeks, porosity dropped to under 3%. It wasn't a miracle of science. It was simple, focused observation, the same discipline that created the engine. Next came supercharger-bearing failures. The high-speed shafts were overheating, the lubricant thinning out and failing under extreme RPMs. Volkov worked with the whole plant's chemists to alter the oil composition, increasing its viscosity. He then redesigned the bearing preload assembly to reduce friction and heat at peak speeds. The failures vanished. Carburetor calibration was a more insidious problem. Units that passed testing on the bench were showing performance drift in the whole air, creating fuel mixtures that could vary by up to 4%. For a fighter pilot, a 4% variance could be the difference between victory and a fatal engine stall. Volkov instituted a new, far more rigorous calibration procedure. It was 3 times slower, but it guaranteed an accuracy of less than 0.5%. The production schedule slipped by 11 days. He was summoned again. He showed them the new data on engine reliability. No one questioned him. By March of 1942, the production line was stable. By May, the first 30 engines were delivered to the Lavochkin Design Bureau. They were installed in an airframe that had been underperforming with its older, heavier engine. The LA-5 fighter. What happened next was dramatic. The LA-5 with Volkov's engine was an entirely new animal. The previous version was outclassed by the German Focke-Wulf 190. The new LA-5 could match it, and at higher altitudes it could pull away. The lighter engine improved the aircraft's center of gravity, making it incredibly agile. Pilots reported, it felt less like flying a machine and more like wearing one. The sheer power gave it a rate of climb that stunned German pilots who first encountered it over the Don River in the summer of 1942. One captured German report described the new Soviet fighter as behaving as if it had swapped its engine in mid-air. In a way, it had. Word filtered back through intelligence channels. The Soviets had a new, game-changing engine. American analysts reviewing performance data assumed it had to be a copy of an Allied design. The possibility that a self-taught Soviet engineer had leapfrogged their own technology seemed too far-fetched. When Western intelligence finally got their hands on a downed plane and analyzed the engine, their report was a model of understated shock. They identified the evaporative intercooling as the key. The American report noted the theory was well known, but had been deemed impractical for mass production. The Soviet engine proved, they wrote, that the practical challenges were not insurmountable. The report did not mention Arkady Volkov by name. It was simply a significant Soviet engineering achievement. Volkov himself was already working on the next version, refining it for better high-altitude performance. He had a proper facility now, with heating and a full staff. He had a team of 12 engineers. He was surprised to find he sometimes missed the freezing concrete room, not for the hardship, but for the clarity. A perfect theory is useless. A working machine is everything. 12 people meant 12 opinions. Government approval meant more committees. Progress was still happening, but it now had to push through layers of bureaucracy. By the end of 1942, hundreds of aircraft carried his engine. By 1943, it was thousands. The engine became the heart of the Lavochkin fighter family, which shouldered the burden of the air war on the Eastern Front. The pilots who flew them never knew Arkady Volkov's name. They knew the engine by its reliability, by the way it started in deep freeze conditions that seized German engines. They knew it by its clean, powerful roar. Many of them owed their lives to a decision made by a stubborn engineer in a frozen room. By the war's end, Over 15,000 aircraft would be powered by a version of Volkov's design. The cold room, the two young machinists, the falling needle on the temperature gauge. From that one moment, a chain of consequence stretched forward, saving thousands of lives and shaping the outcome of the war. Volkov's work didn't end in 1945. He became one of the most important propulsion engineers of the 20th century, eventually leading the design of the jet engines that powered the Soviet Union's long-range aviation for decades. The man who once worked by candlelight with scavenged parts now commanded armies of engineers. The man whose ideas were called fantasy now oversaw projects that his former critics couldn't even comprehend. His NK series of turbofan engines were, by international consensus, among the most advanced in the world. Western engineers studying them saw the same core philosophy: eliminate needless complexity, attack the thermal problem at its source, and design for what can be reliably built, not what can be abstractly imagined. The philosophy never wavered. He was always the man who trusted the gauge over the committee. He was the mechanic who trusted measurements above all else. The original prototype, the one from the freezing compressor building, was eventually moved to the Central Armed Forces Museum in Moscow. It sits there today in a glass case. It doesn't look like a holy relic, it looks like an engine. You can see the file marks on the cylinder block where Yuri had to manually correct a surface. You can see a small, slightly uneven weld on the supercharger housing made by Pavel the day before the first test. It isn't perfect. It didn't need to be perfect. It needed to hold together at 800 horsepower in a freezing room before dawn. And it did. Millions of people walk past museum displays, their eyes glazing over. This one deserves a longer look. It is the physical proof of an idea that was declared impossible, built by a man who refused to believe it. There is a special type of genius that thrives on rejection. Not because they are fueled by spite, but because when everyone says, "It can't be done," they finally get out of the way and leave you alone with the problem. And sometimes the problem just needs to be left alone with the right person. If you found this story of ingenuity inspiring, show your support by hitting the like button for the WWW2 Record Hub. Arkady Volkov was 31 years old, standing in a hallway with a rejected proposal and a choice. He wasn't the most credentialed, the most connected, or the most celebrated. He was the one who went back into the cold and built the damn thing anyway. The needle on the dynamometer swung past 1800. He picked up his notebook and began to write. That is where the legend ends and the history begins.